Every single chemical reaction, whether it's the fizz when you open a soda can or the massive explosion of a star, it's all about one thing: energy. Today, we're going to pull back the curtain and see how chemists can actually calculate that energy, moving from these big abstract ideas right into some real-world math. Just picture the last time you saw a fireworks show. It's absolutely stunning, right? But what you're really watching is a massive chemical reaction that's releasing an incredible amount of energy. But could you actually put a number on it? Could you calculate the exact energy in that beautiful burst of color? Well, the answer is a big yes, and we're about to find out exactly how. So here's our game plan. We'll start with the basics of reaction energy, then we'll introduce our first big concept, enthalpy, which is all about heat. After that, I'll show you a really clever shortcut that chemists use all the time before we ask the ultimate question: will a reaction just happen on its own? And finally, we'll tie it all together with a super powerful idea called Gibbs free energy. All right, first up, let's get our bearings. When we talk about the energy of reactions, we're really diving into a field of science called thermodynamics. You know, thermodynamics has a very specific job. It's a predictor. It can tell us if a reaction is possible, if it even has the potential to happen. But here's the catch. It won't tell us if it's going to be fast or slow. I mean, a diamond turning into graphite is thermodynamically possible, but it takes millions of years. For today, we're just focused on that first huge question. Is it even possible? So, where do we even begin with measuring all this energy? Well, the most direct way is by looking at the heat. And in chemistry, when we talk about the heat of a reaction, we have a special name for it: enthalpy. The best way to think of enthalpy, or delta H, is like a heat bank account for a chemical system. When a reaction happens, a transaction takes place. Either heat is released, that's a withdrawal, or it's absorbed, that's a deposit. And it's this change, this transaction, that we're going to measure. And these reactions really come in two main flavors. You've got your exothermic reactions, like our fireworks. They release heat, they feel hot to the touch, and their delta H is negative because the system is losing heat to the surroundings. Then you have endothermic reactions. They absorb heat, so they feel cold, kind of like one of those instant ice packs. Their delta H is positive because the system is gaining heat from the outside. So how do we actually calculate that change? This formula right here is our golden ticket. All we're doing is finding the difference between the final state and the initial state. We add up all the heat energy stored in the products, that's the stuff we end up with, and then we subtract all the heat energy that was stored in the reactants, the stuff we started with. The difference? That's the energy of our reaction. Simple as that. Now, trying to measure the enthalpy for every single reaction from scratch would be, well, impossible. Luckily, chemists came up with a brilliant shortcut, and it's called the standard enthalpy of formation. Think of it like a giant encyclopedia of chemical recipes. For pretty much any compound you can imagine, scientists have already done the hard work. They've measured the energy it takes to form 1 mole of it, and a mole is just a standard counting unit for chemists, kinda like a dozen, from its most basic raw elements. These pre-calculated values are our building blocks. And here's the crucial rule that makes the entire shortcut work. If an element is already in its most natural, stable form, like the oxygen gas we're breathing or the graphite in a pencil, we just say its formation energy is 0. It's our baseline, our starting point. It's kind of like saying it costs 0 energy to build a brick if you're already holding a brick. This is the foundation for everything we're about to do. Okay, enough theory. Let's put this into practice. We're going to calculate the total enthalpy change for this exact reaction: hydrogen gas plus fluorine gas reacting to produce hydrogen fluoride. So, how do we solve this? Step 1, we find our values. We look up hydrogen fluoride in our chemical encyclopedia, and its formation enthalpy is -271. For hydrogen and fluorine, we use our key rule. They're elements in their standard state, so their value is 0. Easy. Step 2, we plug those into our formula: the total energy of the products minus the total energy of the reactants. So that's 2 times our HF value minus, well, 0 plus 0, which gives us our answer, -542 kilojoules. That negative sign is super important. It confirms for us that this is an exothermic reaction, meaning it releases a whole lot of heat. See? With just a little bit of math, we've just quantified the energy of a chemical reaction. So we figured out how to measure the heat. That's awesome. But it brings up an even bigger question. Just because a reaction releases energy, does that guarantee it's actually going to happen all on its own, without any outside help?
To answer that, we need a second key concept: entropy. You'll see it as delta S, and really, entropy is just a measure of disorder or randomness. A messy room has way higher entropy than a clean one, and a fundamental law of the universe is that things tend to move toward more disorder, not less. The universe just likes a bit of chaos.
So now we have two different forces at play: the tendency to release heat, that's our enthalpy, and the universe's natural push towards disorder, which is entropy. To figure out which one wins in any given reaction, we need a tiebreaker. And that tiebreaker is called Gibbs's free energy. And this is it. This is the master equation. Gibbs free energy, our delta G, is equal to the change in heat, delta H, minus the temperature multiplied by the change in disorder, delta S. This one elegant formula weighs that drive for lower energy against the drive for more chaos to give us the final verdict. And interpreting the result is as simple as it gets. If the final delta G number is negative, the reaction is spontaneous. It'll happen all on its own. If it's positive, it's non-spontaneous. You have to put energy in to make it go. And if it's zero, the system is perfectly balanced. It's at equilibrium.
Okay, we have all the pieces of the puzzle. Let's put them all together and use this incredibly powerful tool to solve one final problem. Here's our final question. Will nitrogen monoxide and oxygen gas react spontaneously to create nitrogen dioxide? With Gibbs free energy, we can find the definitive answer. The process here is exactly the same as our enthalpy calculation. We just look up the standard Gibbs free energy values for our products and reactants. So for our product, nitrogen dioxide, we have 2 moles at 52 each. For our reactants, we have 2 moles of nitrogen monoxide at 87 each, and of course oxygen is 0 because it's an element in its natural state. We plug that into our products minus reactants formula, which gives us 104 minus 174. And that leaves us with our final answer, negative 70 kilojoules per mole. The most important thing here is that negative sign. Because delta G is negative, we can say with absolute certainty that yes, this reaction is spontaneous. It will happen all on its own, no outside energy needed. It's just a fantastic example of how we can use these calculations to predict how the world works on a molecular level. So we've gone from the big, flashy spectacle of fireworks to a predictable, calculable science. And believe me, this isn't just theory. Understanding and calculating the energy of reactions is the absolute foundation for creating new medicines, designing more efficient fuels, developing sustainable energy sources, and engineering revolutionary new materials. The ability to predict what's possible is always the first step toward building a better world.